Oh, be back is here. Okay, good evening. And in some places, it's very good morning. This is tutorial number 12. And the gender, okay, as you can see, I think I've posted homework on ductile yielding. So I'm going to do two examples. One is on how to apply the maximum. So example, on maximum distortion energy. So we will class this as vomices. And then we're going to do another example of maximum shear stress. And this is on Tresca. Okay. So the example I'm going to work on, you can download from Avenue to Learn. Okay, I posted in Avenue to Learn. And I'm going to cut and paste the example question. Okay, so this is our example number 1. So we are given a shaft. Okay, so if we look at the problem, let me shrink it down slightly so that you can see better. So the shaft is 1.5 inch diameter. Okay, so we're given that the diameter is equal to 1.5 inch. And it's made of steel, and the stress, the yield stress, okay, of the steel is also given at 42 times 10 to the power 3 psi. Okay. And we're going to, the first one, we're not going to use the maximum shear stress. Okay, I'm going to do this one first because in the lecture, I did a maximum shear stress example. Okay, so we're going to apply, okay, we're going to apply maximum distortion energy. Okay, we're going to apply maximum distortion energy. And what we're going to find is we're going to find, the question asks that we're going to find torque. Okay, we're going to find the torque. Given that P, okay, the P value is equal to 60 kilo-pounds force. Okay, so I will start drawing our transformation. Okay, so I'm going to call this my X, Y, no, Y is the other side, and Z. Okay, so given how we have labeled, okay, so the torque will be torque along the y-axis, right? And P over here is equal to P along the y-axis also. Okay, so we are given, so we want to find what is our Ty. Okay, and we're going to base it on maximum distortion energy. Okay, so just to quickly recall the maximum distortion energy criteria. Okay, the maximum distortion energy criteria is based on this expression where we have stress A squared minus stress A multiplied by stress B, right, plus by stress B squared, okay, must be less than stress U squared. Okay, so I'm going to call this equation 1. So just to quickly recap, where stress A and stress B are the principal stresses in 3D Mohs circle. Okay, right? So what we are given, if you look at this equation, right, equation 1, on the left hand side of equation 1, okay, this side, stress A and stress B are acquired from structure analysis. Right, the yield on the right hand side is a material mechanical property. Right, so as you can see in the question, this is in fact given. Right, this is in fact given. Okay, as you can see down here. So first of all, we have to pick an element. Okay, find a location. So we're going to pick an element. I'm going to pick an element down here. Okay, I'm going to place my element. Now you can place your element anywhere for this case because there's only a normal stress and torque, and the normal stress and torque is not radius dependent. Okay, so there's a good news. Okay, so now first of all, we are going to construct. Okay, (3D) Mohs circle. Now, in most of the solution manual that you see, they don't do this. Okay, they skip this step. They take something for granted. And I want to show you what did they take it for granted. What is this thing that Eugene say? Hey, they take it for granted. Why is it? Okay, I'm going to plot the 3D Mohs circle first. Then I'll tell you what they take it for granted. Okay, so if we look at 3D Mohs circle, okay, so I'm going to call this my X, my Y, and this is our Z. Okay, so this is our 3D Mohs circle, and this is our element. Okay, so this is our element. So we know there's a axial load coming down, right? We know there's a stress. Okay, this is your stress Y, right? And then you have a shear also, right? So if you look at the torque is going in this direction, yes or no? Right? So the element will want to move in this direction, right? So that is, or the deformation, there's a torque. So if you look at the torque with the direction, so this is the torque in a Y direction, or Y intersecting plane, intersecting the the shear is in the X direction. The other arrow shear, the intersecting plane, is intersecting the X axis. The shear is going to Y. Okay, and then what we can see down here, from here, we know that stress in the X is equal to 0. Okay, stress in the Y, or stress in the Z, normal stress in Z is equal to 0 also. And then there's no shear or whatsoever directions. Okay, so from here we are going to construct 3D mold circle. Okay, we're going to construct 3D mold circle. Just a sketch. Okay, just a sketch. Right. So we're going to construct a 3D mold circle. So we're going to normal stress. Right. Then we have shearing stress. Okay. Then we have I'm going to draw this normal. Element rotate clockwise. Element rotate anti-clockwise. So we know that we have a stress. We have a stress y. Okay, so this is our stress 1. Okay, so this is our stress y line. Right, it's in compression because over here is 0. Then we have our stress x and stress z. They are on the same axis. Okay, stress x. Okay, then we don't know the shear yet. What is the value? But this, as I say, is a sketch. So this is our shear. Okay, so this is our shear line. And this is our the other shear line. Okay, then we're going to label. So this is our point x, right? Point y, and this is our point z. Okay, so we can see we know where's our point z. Okay, so point z is here, right? That's our point z, and then point x. Okay, so point x has a shear. So this shear value, this is our shear xy value. Okay, and then the element is rotating anti-clockwise. So this is our point x, right? And this is our point y. Okay, then we can draw a straight line. Okay, so from here we can construct one of our mold circle. Okay, we can construct one of our mold circle. So this is our first mold circle. Okay, so this is our first mold circle. So this circle, as you can see, this circle belongs to our xy plane. Okay, belongs to our xy plane. Then we have another circle, a smaller one. Right, this is the other circle. And over here, this is for our xz plane. Okay, and this is our out of plane. Based on how we draw the element. Okay, and this is our in plane. And then we can construct one more circle. Okay, so this is our third circle, and this third circle belongs to YZ plane, and this is our out of plane. Now, the reason why we have to construct this, now we know that stress A and stress B, right, are on the in-plane circle, yes or no? So stress A and stress B, as you can see from here, stress A and stress B are in plane, on XY plane, and they are in plane. Okay, they're in plane, right? Then you can use XY plane data, right? Now you know stress A and stress B are on a. Now you guys, so what? Okay, what if? Okay, now this is a what if? Okay, this is a what if. Okay, what if? Right, we have another situation, right? I'm going to, again, this is just a sketch on Moser. We have another situation. What if, so this is our normal stress. This is